ask you to send an email message to this email here, info@6pro.pro, and just remember to put the subject of the message. It's my QForm cloud license and your name. So you're gonna have some control here from the people that wants to do this training, and will receive for sure the cloud version to be installed in your computer. So then you please inform your name, phone number. If you have a company or university, please inform that. But if you don't, that's no problem, all right? And your occupation as well. If you're a student, I'm engineering, I'm a manager, whatever you do. And in case you do not receive, when you watch that in case you do not receive a message from us with the software in about 2 business days, it might happen some problem in the communication. So please really try to contact us by our website, because maybe there is some communication problem there. So please do that. Then we're gonna receive this, and I will ask you guys to enjoy your time using the cloud license. Remember, you're gonna have technical support from us, and also access to additional exercises for different forging analysis types, all right? And you can also make use of your cloud license to simulate other cases of your interest. If you're in a university, you can do some some other tries for your researching. If you're in a company, you can conduct some simulations of your process, your own process, and we are here to help you on that. If you ask me, but you're gonna provide me a week of trying, that might be not enough to approach my own processes, my own projects. I have to tell you guys that after this is just the beginning. After that, of our conversation, we will put this software for a longer period of time wherever you want. If you're in a company, you're gonna send to you, can put in a computer there. If you're in a university, we're gonna talk to you to tell you how to put that in the university, so you can keep using. It's just not this 1 week. This 1 week is important because it's gonna be your first use of the software, and also it defines our connection, our communication. Okay. All right. Now let's talk about the cases. For this short training, we prepared 2 basic cases. Then I'm gonna show you also a tutorial that I have many others. Let's go step by step. All right. So case, we talk about one case of underfilling, also case of lapse, and then just to tell you where the tutorial is. That's very nice, easy to access. Underfilling. Let's see here on the left, it's the initial technology for the forging, and you can see on the right the optimized technology. But why? What happened? You can see first here, show you, this part is different from this one. This one is well finished. This one there's an underfilling. It doesn't fill the dies, right? And you can see that there is more material here in the flash than here. So more material went out of the part, the final part actually, and because there are some problems of underfilling problems. So it can check also here, also there, and there. All right. So let's show here how you can simulate that. Oh, by the way, I'm gonna just show 2D simulations because they are faster. but you can conduct 2D and 3D simulation, of course. Initial technology, optimized technology. You can see points of underfilling. Okay, all right. And also you can use those blue dots for be really sure that there's no touching. And the optimized technology is on the right side. Initial technology, you can see there's an offsetting operation. It's a 2D, right? This is a axisymmetric line because this is symmetric, around there. It's round, and the offsetting. Then you have this preform, and this preform. I mean, there are some problems here. You can see here under filling also. This dot, this red dot here, a red shows you some lapse, okay? And this is not the objective of this case, but you already can see that. And then you go to the final forging, and you can see under filling here, here, and here, there's also one there. And you can see that for under filling problems, you have to pay attention to the preform, okay? Because we need more material here and more material here, also a little bit there. But so actually, maybe if we increase the amount of material in this part and try to, to flow more material to this part as well, that's what I need when you think about the final forging part. Okay, so we're gonna basically change this preform here. See, initial technology, optimized technology. So we increase the amount of material here and also send some material to here. When you check the final part, you can see there is no problem. All right, it's fulfilled. All right. And basically what we did was we changed one of the operation. We changed the die geometry. So the modification was here on the left you can see the preform, on the right you can see the new preform. The type of problem can be 2D axisymmetric or 2D longitudinal, but when we do like this, we save time. You say to the software, all right, this is round, okay, so you just say it's 2D axisymmetric. And you can conduct that. We're going to provide you guys the geometries and the software, okay? But here in this slide 26, you have all basic information you need. Actually, they are here. All basic information you need for conducting a simulation. And I'm going to show this here slowly, so you guys can understand that. I'm going to just do this initial, then you can conduct the optimized. One thing that I want to tell you is that I'm going to show it here. You still don't have the license, probably by this time, and we're going to send that to you. But when you go try it by yourself, understand that you have a step-by-step FE setup here. Well, starting from the slide 27, you can see first create a new process. So you go there and create a new process. Then define problem. So it's step-by-step. Click forward. You're not gonna have problem. If you have any kind of problem, just let us know. I'm gonna help you right away. Okay, then you can see like step by step. Okay, I'm gonna concentrate here in this slide 26, and you guys are going to have a PDF with this presentation, so there's no no problem for you guys to conduct the simulation. I just opened my QForm cloud, all right? You have to remember that you're gonna have to conduct some settings. You have to, let's say, validate your license. We are going to send a specific password for your license. And so you're gonna have your own license, and you have to come here, server settings, okay, and we will have to check the status of your license, right? Here you're gonna put a login, password, and test the connection, all right? And have to go there, and you're gonna tell you, okay, connection established. And if you do that, your license will be working very well. All right, so let's go back to our first case here. So I'm gonna create a new process. All right, now I'm gonna change the problem type to a 2D axisymmetric problem, and I'm going forward. Now I will load files, load the geometries that you are also going to receive. And when I go here, see, I'm gonna choose this initial, and you can see I already have the top die, billet, bottom die. Okay, it's all here. All right, and go forward. Now I'm going to select the material. I have to remember which one. If you go to the slide 26, you're going to see it's 1045. Initial temperature that comes from the furnace, it's 1200 Celsius. Okay, so the material here, I'm going to pick 1045. Assign it. You can see it's already assigned there. And now you let me close it. 1200 and forward. Now it's time to set the tooling. All right. So for tool 1, you can see here is also by orange here. Tool 1, my presentation is say, okay, consider a mechanical press with 25 meganewtons, and that's what I'm gonna do. So I have a lot of information here. So I'm going to the mechanical process. There's this one, mechanical press, sorry, there's this one here, and assign that. So you can see, because actually it's my upper die that is a top die that is attached to the press, so we will have this movement, and the bottom die is going to be fixed plus OZ. Okay, two clicks here, it works. Assign here also works. All right, lubricant, I'm going to choose a lubricant, hot forging, steels, graphite plus water. Material, it's a A13, right? A13, and also there is a heating of the dies. Let me check here again. It's 300 Celsius. All right. So the dies are preheated. Okay, that's it. Now I can go forward. And what is the stop condition? There are many stop conditions here on the left. When you check here, it is for operation 1, 108. Okay, stop condition. So let's do this. Distance 108. All right, and you can go forward. And that's all. By this time I can, there is also then this blows, because the part comes from the furnace or for the induction heating process, and it has a transfer, right, and the cooling in the air. Then after cooling the air in the transfer time, it cools also when it's on the tool, on the die, because it changes heat by conduction. So let's say the furnace is very close to the press. So I'm gonna just put here 1 second. You can put 2 seconds, 5 seconds, and then 1 second by cooling on tool. So it's one here and also one here. All right, let's click OK, and let's start the simulation. Restart. Yes, and I'm gonna save here. Upsetting. All right, I saved somewhere in my computer the results, and here we can see it working. It starts connecting to the license server. Something that's important here, I'm watching the FE setup, but here if I go to the right, I can see the simulation, and I can even work and go forward and backward on my simulation. See, you can also see in a 3D. Okay, this is my part here. I can turn off the dies or the part if you want. I can also make it like this, and goes. You can watch on a part the temperature distribution, plastic strain, effective stress, mean stress, flow stress, here's different, and the strain rate also, vectors of speed, of velocities in the vectors. So you can see how it works, and you can see for any type of part that you're going to forge. Okay, and also have this type of visualization. It's interesting because you can also let's say here I want to see the press load, so you come here to this graph, okay, and also can let's see the load by the displacement of the top die. So displacement, all right, and you can see the load, okay, during the process. More than that, also you can track, like putting a sensor there. You can track any point in this. You can do this. Let me put like this. So you can, for example, to see. Let's come here. Track points and lines. So I can track any point anywhere I want. I also would like to see the fiber deformation. Okay, just put some fibers here. Okay, vertical or horizontal here, and you can track this. All right, and you're going to see what's going to happen. Right, so you see the fiber deformation, you see the points here. For example, let me do another analysis here. I'm going to consider this point 1, and what was the plastic strain there in function of the die displacement. So you can see that the plastic deformation increase, of course. I'm going to also put the other one, the 0.2. So 0.1 had a bigger, let's see which one is, this is 0.1. Interesting, 0.1 had a bigger deformation. And I'm going to put on the right side of the graph, not plastic, but I'm going to consider temperature for 0.1. So you see that as it deforms, it strains, the temperature increase. Let me also see for 0.2. Okay, 0.2. I also have it, temperature, and both increase because both are increasing its plastic strains. You know, so you can create, then you can export that and analyze that. It's good for understanding the process. It's good for conducting your researchings and so on, and also propose solutions to a process. All right, so this is the first case. It's all well shown in the next, you see step-by-step instructions here. All right. Okay, now let's go to the second case. It's a lapse prediction. But this time we're going to use this part here. This is this billet. I have top die, bottom die, and you see we're going to use now a hammer. So you do many blows for forging this part. And you can see the part forged here, top view, side view, front view, and you can see this. Here we position it all in a very good 3D simulation. Okay, we position that here. Here we have this indicative of lapse. And then you can see here, if you see only on the surface, you're going to see a line because of the lapse that you can see on the surface. It's only a line, but it actually goes inside the part. Okay, so when you go to the practice to the right, you can see that there is a lapse here. They had already changed the tooling we used for simulating, trying to solve that, but it was still there. So you can see here, it was still there. It's there, but it's different. It's not concentric, it's eccentric. You see, when you see that in the practice, you can see that. It's different from what we simulated. Why? At least we did one first simulate with not modified tooling geometry, all right? And we got that. We got the problem right in the first simulation. When you check here, let's talk about some influence, aspects of influence in the forging. Okay, let's say when you position the billet, it's important. So you can see there is no reference for positioning the billet there. It's important to have this reference. You have also a billet geometry precision when you cut it. Also, the surface of the billet might be with some problem that might have a slope that might influence on the processes. The dies might have a slope during the assembling. Also, they might be not aligned. Top die might be with some problems during the assembling. Die wear, it might wear more from one side than the other, and then it creates differences. It's possible. Also, friction coefficient variation, temperature variation, strain rate might change that, and many others. Here I'm gonna just talk about one of them, It can happen in only this one, but it can happen many of those combined, okay, at the same time. And you can see there is no positioning reference. So just put 10 millimeters to the left here, because it's possible. The guy there, he holds this part at 1200 Celsius, and of course he is not going to position that very well, I mean very precisely, because he has no reference. And then you check, when we did that, when you simulate that, you can see already that there is the lapse is already not concentric. You see, as it happened in the pretzel. However, in the pretzel I have others aspects of influence altogether, and I can work on my simulation the best I should, or I can use my simulation to understand the problems and to make it more robust, or that can absorb any problems for the billet, the dice, positioning. So I have to be able to prepare my process and forging process in a way that this thing won't happen in the pretzel. So this is very important. And here you will have this case for you to simulate by yourself. Here are the data that you should consider, and also have different exercise simulation A, B, C, D, and so on. All right, and then of course you have the step by step you need. Okay, so let's see here. Let's do this project. I'm going to create a new process. All right, it's going to be 2D. Be faster here. Go forward. Now let me get this 2D here. As you can see, top die, billet, bottom die. Just go forward and I'll select the material. Let me see which material it is. It's a 1020 1200. Alright, right. One thing that you can put the material naming in any standard you want, right here. 12. Okay, go forward. It's good that you can move the windows so it can be more convenient for you. Top die, it's a hammer. Which hammer? It says here it's 5 tons. Alright, so I'm gonna get this 5 ton hammer, a sign, and bottom die fixed, lubricant, the same here, material H13, preheat, what this is, 200 Celsius. All right, and okay, go forward, and the final distance, stop condition, it's going to be a distance of 5 millimeters. 5 millimeters. All right, just like that. Go forward, it's everything the same, and blows. Okay, I will consider here 5 blows. Depending on your process, you're going to need more blows or less blows for for the hamming process. So 5 for me here is going to be okay. And in the here I say, okay, see detailed instructions, because I just ask you to consider those 5, maybe 8. It doesn't matter how many you put. If you put like 10 blows, it will stop by the stop condition that it's 5 millimeters. So you're gonna actually see how many blows you would need to conduct the simulation. Okay. So first of all, what I'm considering here is that cooling in the air takes 3 seconds, then cooling on 2 is 2, and then you can consider whatever you want between blows. Okay, and there's also energy share. I'm going to put like 90, 80, 80, 70, 70. You can modify that the way you want. And all right, so 3, 2, 90. So here, first one is 3 to get into the hammer, 2 to start the process, 90% efficiency. Then with 80%, 80%, 70%, 70%. All right, go forward. That's it. And let's simulate it. It's contacting the server. Let's remember that you change the arrows here, you can see. Oh, now it's on the second blow. You can see here the blows. It works for the first, now it simulates the second blow. It's very nice. When you're gonna check the results, you can go forward and backward on the blows, and each blows you have to go forward and backwards. Okay, in a second. You can see actually here it's going to have a problem here, because it ran the first blow, and then this part of the workpiece touched first top die, and will keep going, and this surface here will fold on the surface here, so we will definitely have our lapse here. Okay, I'm going to stop this one here, and to conclude our short training, let's go to the tutorial. So you can go to the tutorial, and there are many others examples there, cases. So you're going to learn more and more. So if you go to the help menu, help, you're going to see there the tutorial, and you have several, and it's also step by step. Okay, and also the geometries are already in your software folder, so you just have to follow the instruction step 1, 2, 3, and you will be able to simulate this software. It's like one problem for conducting die analysis is very nice. 3D, many other types of defects, fatigue. It's also interesting to see the number of cycles to crack your die. And all right, that's it. Thank you for your attention, and me and my team here, we are really waiting for your email message, so you can receive all information and the software for already practicing the simulation. You'll have a good day.